Hey everyone, so in this video we're going to be going over the 2022 AP Physics 1 International Exam, the first FRQ, and this one has to deal with a simple harmonic motion and energy, so let's just get right into it. So the question states the following two scenarios describe a cart that is attached on either one or two identical springs. So the first scenario has one spring and the second one has two springs. But other than that, it's the same scenario, right? It's the same cart. It looks like there's negligible friction. And then it states that the distance away from the equilibrium position, which is defined as x equals 0. And the left is defined as the negative, which is the maximum distance away alongside that positive direction. All right. And it says in scenario 1, the cart is attached to the wall with one spring as shown. So we're talking about this example right here. The total mechanical energy, so we're just going to assume the total energy in the system of the cart spring system, okay, in scenario 1 is E1. All right, that's an interesting variable. So the first question wants us to derive a expression for the kinetic energy. The kinetic energy of the cart in terms of E1. I want to switch colors here. Let's use this like pink color. When the cart is at this not equilibrium position, this position of x equals positive a over 2. So that position I want to define here real quickly is going to be in between that equilibrium position and a, right? Because a over 2 is right here. So when it is there, well, the first thing I want to know is that when it's, let's say it's in movement in simple harmonic motion, when it passes that equilibrium position, it's going to have its maximum kinetic energy. And then when it passes through one of these maximum points, that's when it has its greatest like spring potential energy. And so if it's somewhere in between, we know it has to have both kinetic energy and spring potential energy. The first thing I want to write down is the total mechanical energy. In our case, they already told us it's equivalent to the cart spring system in scenario 1. So that is going to be the total spring potential energy when it is at A. It doesn't matter if it's positive or negative, because here we can see that in this system it's at negative A, and so it's the maximum distance away. So this cart could have been like over here and would have had the same like energy. So if we want to derive this expression, we're going to have to find that new spring potential energy, because that spring potential energy is not going to be the same amount since it's a different position away from the equilibrium. So we're going to get something with the new total energy is going to be equivalent to our spring potential energy, which I'll just write out as 1/2 k x squared. And then we're also going to have kinetic energy, 1/2 mv squared. So we know this value right here, right? This value right here is going to be basically representing the spring potential energy when it is at that new position that is defined as a over 2. And so now we need to find what that is. So we can rewrite that as just the same thing, 1/2 k. And a, in our case, that would just be x. That can replace x, and that can really have any value. And you'll see in a second how we can use that comparison strategy between the two. So let's just write a over 2, right? And that is squared. And so if we compare this to our original equation, the one where the total mechanical energy was all spring potential, the spring potential energy at A, or really it was negative A, but interchangeable really, that's equivalent to 1/2 k A, right? Because that's the maximum distance away. So that's also squared. So now we need to just find the distance, well, not the distance, the factor between these two spring potential energies. So to do that, we can just plug in a fake value for A. And I'm just going to plug in 1. So for this one, we're going to get 1/2 k 1 over 2 squared. And that is going to give us 1/2 k times 1/4. So that's equivalent to our spring potential energy when it's at that new position. And then for this one over here, 1/2 k and then a squared, or not a, 1 squared. 1 squared is just 1. So we can keep it like that. And that is equivalent to our original maximum spring potential energy. So now if we compare these two, we can see that the 1/2 cancels out on both sides. The k's cancel out on both sides, and we're left with 1 versus 1/4. So in order to get from our original 1 to our new 1 is a factor of 1/4. So with that factor, we can represent it as this. Shift everything. E1 equals 1/4 spring potential energy. And now we want to add that kinetic energy. So now we want to figure out what that kinetic energy is. And we know that since it's simple harmonic motion and there's no friction, since it's negligible, then energy has to be conserved. So it has to add up to 1. So our kinetic energy is 3/4 ke. And that is our expression that represents kinetic energy in terms of E1. Let's move on. So as shown in the figure for scenario 2, there's a second identical spring that's attached, yada yada yada, and wants us to determine the total mechanical energy of the cart spring system in scenario 2 in terms of the total mechanical energy of 1. So if we look back at this situation, we said before it's the exact same thing except now we have 2 springs. And so if you have more springs, that means more spring potential energy. All right. So if you write this out, scenario 1 is just the total mechanical energy would just be that. But then for scenario 2, we would have a coefficient in front of E1 is the total of E2. And so since there is 2 springs, right, there's 1 spring here that's providing that initial spring potential energy. Now we want to compare it and see how that spring potential energy or total mechanical energy would change since it's at its furthest point. So all of its energy is going to be spring potential energy. We have 2 springs now, so that's double the energy. And so our answer here would be 2E1 equals E2. All right, let's move on. The maximum speed of the cart in scenario 1 is V1, and the maximum speed of the cart in scenario 2 is V2. Calculate the numerical ratio V2 over V1. All right, so let's just write out what we know. So scenario 1, scenario 2. We know scenario 1 has E1, like that's its total energy. So if this is its total energy, and it says its maximum speed, so when it's maximum speed, it's passing through its equilibrium position. So we can set this equivalent to just kinetic energy. All right, let's just call that kinetic energy. We know scenario 2, it has double the energy, and so now it has double the kinetic energy. Now, double the kinetic energy, let's use that. So 2x the kinetic energy does not necessarily mean 2x the velocity or the speed, right? So we can use the comparison strategy. All right, so now let's write out the kinetic energy formula, which is 1/2 mv squared equals kinetic energy. So now we want to isolate for that velocity. So to do that, we'll just take the total kinetic energy 2 over mass. Square root of that is equivalent to velocity. Right? This is the original one. This is if the kinetic energy has a coefficient of 1. So if I compare this to that second scenario, so this is scenario 1. So scenario 2 would be 1/2 mv squared equals 2 ke, because the kinetic energy is doubled, the total mechanical energy is doubled, and therefore that kinetic energy, since it equilibrium position is double as well. So if we were to just isolate for our values, what we'd get is 4ke over m. Square root of that is our velocity. And so now we can just compare these two velocities. So if we look here, and let's use red. The masses are the same, so we can just cancel that out. And the kinetic energies are the same, except the coefficients, but we'll just cross those out. So now we're left with this value of square root 2, and this value right here is square root 4. So what does this tell us? Well, what this means is the difference or the scale factor between these two will tell you the ratio. So to get from square root 2 to square root 4, you would multiply it by square root 2, right? Because square root 2 times square root 2 is just 2. And the square root of 4 is 2. So, since we have these two over each other, we know that the ratio would be square root 2. Alright, so for this final example, it says the student correctly sketches a graph of the horizontal component of the net force that is exerted on the cart by the spring in scenario 1. So now it wants us to do the same thing except for the cart in scenario 2 for that net force. So if you look back at the diagrams here, you can see that the only thing that's really changing is adding that spring, and as we determined in the last question before, that adding that spring changed the total mechanical energy, and that's important because we can actually determine the force, which would help us draw that diagram using the work equation. So work is equivalent to the force times the displacement, if it'll let me write. So the displacement is constant, right? Because it's in simple harmonic motion, so it's just going to go back and forth. So it's the same thing for both scenarios. The only thing that's changing is there's an extra spring, which provides extra energy, and that is tied into work, which is also represented as change in energy. All right. So that change in energy will help us find that force. And I'll show you a quick example. So let's just use fake numbers. So let's just say scenario 1, right? And scenario 2. So, dang, this is really hard to write right now. OneNote does not want to cooperate. But anyways, let's say the work was 5 joules. And we don't know the force. And D, like we said before, was a constant value, which we will hold constant between the two equations. Let's say it's just 1 to make things simple, right? So this is going to stay constant. So now the force, we can easily solve. 5 times 1 is 1, is 5 newtons. So now if we double this energy, right, because that's what we did in our scenario, if we double this energy to 10 joules, what is that force? Well, we know D, the displacement, will stay constant, and so it just happens so, that this will also double. So the force doubles when the energy doubles in this case. It's not always, but in our case, using the work equation, that is the case. And so now we can just double this. So we can just draw it one box above because it's double the force, assuming the same scale. Plot our 2 points and just draw a hopefully straight line across. That's not a great drawing, but as long as it proves the point of doubling that force, it should do. So yeah, that does it for the video. Hope you guys learned something. If you guys have a question, drop it down below in the comments, and thank you for watching.